This equation is what's called a hyperboloid, which is you have this hyperbola and you rotate around this way. So it's a surface of a revolution. And you can actually use some calculus 2 method to find the surface area. There's a formula in a calculus 2 book. But I want to show you how to use the calculus 3 method to do this integral. Now, in order to do that, we first need a parametrization. And the way you're going to parametrize is, first think of x squared plus y squared as 1 plus z squared, so that x squared plus y squared is equal to square root of 1 plus z squared squared. And the reason I write it like this is because this tells us that every level at level z, any cross section, it's going to give you a circle of radius square root of 1 plus z squared, right? So this is a circle of radius. This r is square root of 1 plus z squared. Now, what that means is that I can parametrize this as x equals to, well, the usual way that you parametrize the circle is x equals to r cosine t and y equals to r sine t. And it's going to be the exact same thing except that instead of r, we're going to be using this. So here's our parametrization. I want to say that r, this r is a different one from this r. It's just the parametrization of the surface. And we're going to say rt comma z is going to be the x-coordinate will be square root of 1 plus z squared cosine t, just like this one, except that r is replaced by that. And square root of 1 plus z squared sine t. And then z would be z. So x comma y comma z that satisfies this can be written in this form. And you can check that if you plug these three things into here, it will automatically be satisfied. Okay? All right, so because this should go around the full circle, we know that t should now be between 0 to 2 pi. And therefore, the surface area that we want would be the integral from 0 to 2 pi for the t and negative 1 to 1 for the z of partial derivative of this this parametrization with respect to t cross partial derivative of r with respect to z, and you take the norm of it and then dz dt. That should be giving you the surface area. Okay, so let's actually do the derivative. First, derivative of this thing with respect to t is, well, z doesn't have any t there, so this is going to be considered as a constant when you do the partial derivative. So that part is going to give you 0. So the only thing that gets really differentiated is cosine t differentiates to negative sine, sine t differentiates to positive cosine, so you get negative square root of 1 plus z squared sine t square root of 1 plus z squared cosine t comma 0. And then you have the partial with respect to z, and the derivative of square root of 1 plus z squared is, well, the derivative of square root is 1 over 2 square root of 1 plus z squared, but then the derivative of the inside function by the chain rule gives you 2z, 2 cancel, so you get z over square root of 1 plus z squared. So that's going to be your derivative of these functions with respect to z. So you're going to get 2 over square root of, actually, z over square root of 1 plus z squared sine t, actually cosine t. And then this one, when you differentiate, same story. And then sine t comes down. And when you differentiate z by z, you get 1. Okay. Now we have to take the cross product. And I should really be doing cross product ijk like that. Ijk. And then you have to do the determinant, right? But since it's going to just take too much time, let's just do it on the spot, okay? So if I expand the determinant with I, when we do the determinant, then I will be multiplied by the determinant of this minor matrix. The determinant of this matrix is this times this minus this times this. 0 times anything is gone, so you only get this. So what you have is going to be your cross product is going to be square root of 1 plus z squared cosine t for the x component. And then now we have to go to the j. For the j, it's these, but then the checkerboard of signs also apply to j so that there should be a minus overall. So it's negative of this times this, and this times this is 0, so that doesn't count. So you only get negative of this times this, so you get plus square root of 1 plus z squared sine t j. And then finally, when k is picked, is the determinant of this. When these two multiply, notice that square root of 1 plus z squared and square root of 1 plus z squared will cancel, and you're just going to get negative z. So it's going to be negative z sine squared of t, and then minus z cosine squared of t. Okay. But if you factor the z out, what's sine squared plus cosine squared? That's just 1, right? So you see that this one here really is just negative z k hat. And therefore, when you take the norm, which means you have to take the squares of each component and put it inside the square root, this will be square root of square of this thing, so 1 plus z squared times cosine squared t. Then squaring the square root gets rid of the square root, so you get sine squared of t, and then finally you have negative z squared, which is positive z squared. The negative squares to a positive. And notice again, if you factor the 1 plus z squared out, cosine squared plus sine squared is 1. So this simplifies to square root of 1 plus z squared plus z squared, which is square root of 1 plus 2z squared. Now that's actually a quite challenging thing to integrate. It's not impossible, but you could do it. There are probably like two different ways, either using the tangent or you can use the tangent function to integrate this, or you can use the sine hyperbolic. I like the sine hyperbolic method better, so let me do that transformation. So the key is to first write this as 1 plus square root of 2z squared, and then use the transformation that square root of 2z should be sine hyperbolic of some u. Okay, so this is the transformation you need to do in order to change the integration by dz. So you're going to differentiate both sides because I need to know what to change for dz. So you get square root of 2 dz. Derivative of sine hyperbolic is cosine hyperbolic. And then you get du. So by dividing by square root of 2, you see that dz is this thing. Moreover, when this z becomes 1, you plug in 1 and you see that square root of 2 becomes sine hyperbolic of u. So another additional data is that when z is 1, u must be inverse sine hyperbolic applied to square root of 2. Okay, now we're ready to do the integral. Okay, this integral is now, let me first use the fact that this shape is symmetric with respect to -1 to 0 has the same shape as 0 to 1, right? So we're going to use that to just double the integral from 0 to 2 pi and from 0 to 1, okay, for dz. But then when z is 0, u is 0, so 0 is okay. But when z is 1, u is this value, sine hyperbolic inverse of square root of 2. So we're going to put sine hyperbolic inverse of square root of 2 here. And then now I can replace 1 plus square root of 2z as, replace square root of 2z as sine hyperbolic of u. And then dz is now replaced by 1 over square root of 2 cosine hyperbolic of u du. This much is your dz, and then dt. Now notice that this has nothing to do with dt, so I can just think of this entire thing as a constant, and if you integrate by dt, integrating a constant by dt from 0 to 2 pi just introduces a factor of 2 pi, right? So let's just take care of the dt first. And then another thing is 2 over square root of 2. If you divide 2 by square root of 2, and you rationalize top and bottom, then this becomes 2. So these two are the same, so you just get square root of 2. Okay, so you're going to get square root of 2, and then 2 pi is going to come out. And then you just have to do this integral, 0 to sine hyperbolic of sine hyperbolic inverse of square root of 2. And the reason I like this is because we know the identity that 1 plus sine hyperbolic squared of u is cosine hyperbolic squared of u. So we can use that, which gives you cosine hyperbolic square root of u inside the square root, and that's perfect because this squared and this square root is going to cancel each other, so that's gone. I already pulled out the 1 over square root of 2 outside, and I have cosine hyperbolic of u du. dt is gone. Okay? So now that's much more tractable, and that's going to be 2 times square root of 2 pi, integral from 0 to sine hyperbolic inverse of square root of 2. And that's going to be cosine hyperbolic squared of u du. Now, we love to use cosine hyperbolic and sine hyperbolic because they satisfy all these trigonometric identities, just sometimes the signs are different because this is hyperbolic trig functions rather than the regular trig functions. So this one can be replaced by cosine hyperbolic 2u plus 1 over 2, just like the usual, see, cosine square root of x is equal to cosine 2x plus 1 over 2. There's this one, so there's a version like that for the hyperbolic. But if you didn't know that, that's fine because you can just write down the formula explicitly. So cosine hyperbolic of u, by definition, this is the definition of the hyperbolic functions, right? So if you square both sides, you end up with this square, which is e to the 2u, this square, which is e to the negative 2u, but there's a double the product. You multiply these two, and these two are reciprocal, so if you multiply, they cancel, and it's double the product, so it's 2 in the middle. And then if you look at this, that is really cosine hyperbolic of 2u, and then this much is, sorry, if you square the 2, this is going to be 4, right? So there should be a 1 over 2 there, and then 2 over 4 is 1/2. So that's what you're going to need, which means you get 2 radical 2 pi. This is going to be replaced by that. If you integrate cosine hyperbolic 2u, that's sine hyperbolic 2u. with the 1/2 in front. Oh, there's a 2 in the denominator, but let's just use that to cancel this 2, okay? So once those 2 are gone, cosine hyperbolic 2u integrates to sine hyperbolic 2u with the 1/2 because of this 2u. And then 1 integrates to u, and then you plug in sine hyperbolic inverse of square root of 2, and then 0 here, you plug that in, and the answer will be square root of 2 pi. Let's pull the 2 out again, so it would be 2 here. And then when this goes in here, unfortunately, no, let's not do that. There's another identity in the trig world, which is that sine 2x is 2 sine x cosine x, right? So you can check that there's a version in the sine hyperbolic world which is the same. So yeah, this is gone, okay. So what I'm going to do is I'm going to rewrite this as sine hyperbolic of u times cosine hyperbolic of u, okay? So that's going to be square root of 2 pi, 2 sine hyperbolic of u, cosine hyperbolic of u is same thing as sine hyperbolic 2u, but there's a 2 downstairs, so these are going to cancel, and then plus u, and then we're plugging in sine hyperbolic inverse of square root of 2, and then 0. And then when this goes in here, the sine hyperbolic and sine hyperbolic inverse cancels, so that just gives you square root of 2. So it's going to be square root of 2 pi, square root of 2, cosine hyperbolic of sine hyperbolic inverse of square root of 2, and then plus sine hyperbolic inverse of square root of 2. All inside this parenthesis where you multiply square root of 2 pi. Okay. So that's the answer. And I think that's a good answer, but you know, some people might want to simplify it even further. So if you want to, if you're a purist and you think the answer should be as simple as possible, there's a way to do this. So let's think about what this is. Sine hyperbolic inverse of square root of 2. Let's call this as x. That means square root of 2 would be sine hyperbolic of x. And that's going to be saying the definition of sine hyperbolic is e to the x minus e to the negative x over 2. So if I multiply by 2, and then if I do a substitution as t equals to e to the x, then you get 2 times square root of 2 equals to t minus 1 over t, because minus is a reciprocal, right? And then you multiply t both sides, so it's 2 radical 2t, t squared minus 1. Move this to the other side, you get t squared minus 2 radical 2t minus 1 equals to 0. And then you can solve this by using the quadratic formula. So it's t would be 2 radical 2 plus minus square root of 2 radical 2 squared would be 8 minus 4 times 1 times negative 1 over 2. And this is 2 square root of 2 plus minus 2 square root of 3 over 2. And these cancel. And then another thing is that it can't be square root of 2 minus square root of 3 because we know that t is positive, right? So we know that t must be square root of 2 plus square root of 3. And because t is e to the x, we have this nice identity that x is equals to ln of square root of 2 plus square root of 3. And this is really the sine hyperbolic inverse of square root of 2. Okay, so we figured out the value of this part at least. But then what does it mean for cosine hyperbolic of sine hyperbolic inverse? Well, now let's think about that. So if you had cosine hyperbolic of sine hyperbolic inverse of 2, that's going to be cosine hyperbolic of x, right? But we actually know what x is. X is this thing, right? And we also know that e to the x is square root of 2 over 2 plus 3. So we can say that since cosine hyperbolic is e to the x plus e to the negative x over 2, and I know that this is square root of 2 plus square root of 3, and e to the negative x is 1 over square root of 2 plus square root of 3 over 2. And this one I can multiply by the conjugate, square root of 3 minus square root of 3 minus 2. And see that this just becomes 1, and square root of 3 plus square root of 3 is 2 radical 3. Whereas this minus this will cancel, so it just becomes square root of 3. So amazing. This value is just square root of 3. Okay, so we're very close now. The final answer, therefore, the surface area, is this thing, square root of 2 pi, square root of 2 times square root of 3, plus ln of square root of 2 plus square root of 3. And you can multiply this out, and I guess this is enough. I guess just rewrite this as square root of 6. That's it. That's the final answer.